Okay, so just have a look at the next question under page 15 now. This is June 2018 P42. So right now, the first part of the question is asking you to use one of the assumptions of the kinetic theory of gases to explain why potential energy of the molecules of any ideal gas is zero. So this one, we should really know by now, after so many times of doing the same thing. The reason why your potential energy of molecules would be zero is because there are no intermolecular forces. Okay, there are no molecular forces between the molecules, so no potential energy. Okay, you just writing no intermolecular forces should be enough already. Okay, then if you move to the next subsequent part, let me zoom out a little from here. Okay, so next part is us telling you right now that the average translational kinetic energy EK of a molecule of an ideal gas is given by this expression, where it is half mc squared equals to 3/2 kT, where m is the mass of a molecule and k is your Boltzmann constant. State the meaning of the following symbols. Okay, so for some odd reason, your past year exam questions tend to like to ask you, how do you write out this symbol in words? Okay, so as mentioned to you in the last lesson, is called mean square speed of the molecules. The wrong answer to use would be this one. If you say it is mean speed square, this is wrong because it's saying this. Okay, it's a different symbol than this, completely different meaning also. Okay, so it's mean speed square. But if let's say you have trouble remembering whether it's mean square speed or mean speed square, your best way forward will be probably to just write something like this. Mean of the speeds, mean of the squared speeds. Okay, you can try to literally write it in words like this, mean of the squared speeds. It will also mean this now. All right, that is your last resort if you do not remember which of these two are you supposed to write. Okay, then the next quantity here is T. This one is thermodynamic temperature. You can also call it as absolute temperature. You can also call it as Kelvin temperature. Just pick either one. All right. So now move on to C. If you move on to part C here, you have a cylinder that is at a constant volume of 4.7 times 10 power 4 centimeter cube that contains an ideal gas at the pressure of 2.6 times 10 power 5 Pascal and the temperature of 173 degrees Celsius. This gas is heated and thermal energy is transferred to the gas that is worth 2,900 joules. The final temperature and pressure of the gas in T and P are illustrated in the figure below. First, calculate the number n of molecules in the cylinder. So this one, usually you have a choice between PV equals to nRT or PV equals to nKT. But you generally won't use the first one because this n is number of moles. You could use this, but it's just more tedious because from here, you will need to find out the number of moles. And then from there, you need to use n equals to n over Na, where n is equals to number of moles times with your Na. So there's actually an additional step here. This is actually more tedious. You generally won't use this. Instead, you will use the second one, PV equals to nKT, because this one is already the number of molecules that you want. So you use PV equals to nKT. You know the pressure. You know the volume. It's in centimeter cube again. Again, remember to change it to meter cube by multiplying 10 power minus 6. Your number of molecules, n, is what you want to find. Your Boltzmann constant is something you get from your data sheet. And then your temperature is 173 degrees Celsius, you need to change it to Kelvin. Either you plus 273.15 or you just plus with 273 only. Both are okay. All right. Eventually, your final answer would be n equals to 1.98 times 10 power 24. All right. This is a pretty straightforward question that's worth 3 marks. Now, then you move on to the next part. Okay. If you now look at the next part, they are now asking you for the increase in average kinetic energy of the molecule during the heating process. Okay, so they want to find the increase in average kinetic energy of a molecule, of a single gas molecule during your heating process. All right, so based on what we've done just now, we've actually did derive some sort of equation that tells us the change in average kinetic energy of a gas molecule. That one is actually this part here. Remember, we say that the kinetic energy of a gas molecule is 3 over 2 kT, such that the change in kinetic energy of a gas molecule would be 3 over 2 k delta T. But you won't be using that one here right now, although they are asking you for that thing. You cannot use this equation right now because if you try to imagine right now, if you use that equation, there is something missing here. You do not know the temperature change, okay? This one is unknown. Although this one can be used to find the change in kinetic energy of a gas molecule, you cannot proceed with this because you do not know what's the change in temperature. If you look back at the earlier part of your question, they mainly told you that it started at 173 degrees Celsius, but then the final temperature is unknown. So your temperature change is unknown here, unless you specifically find it out. Okay, so you can't proceed with this. So how are you going to proceed if not with this equation? This one you have to relate to definition of internal energy now. If you look at the top part of the descriptions here, it was mentioned here that internal energy is the sum of KE plus PE, such that change in internal energy is equals to the sum of your KE change plus PE change. But we already know by now that ideal gas does not have PE. So your change in internal energy is really just the change in your KE alone. This one is actually this part here that I've just derived for you earlier. Okay. So this one is one. This one is from definition of internal energy. So the next thing that you want to relate to is thermodynamic first law, where you say that increase in internal energy is equals to work done on system plus heat supplied to system. This one here, sometimes internal energy is represented as delta U, okay? So sometimes you may see me writing it as a different symbol, but both of these are actually referring to the same thing, okay? So right now, I want to look at the heat supply to the system and the internal energy. Okay, the heat supply to the system is really known to me. It's 2,900 joules. Okay, and the internal energy change of my system is actually related to my kinetic energy change. Okay, so there's one thing here that is somewhat unknown. That one is your work done. Now your work done here is actually 0 because your volume is constant. How do I know my volume is constant in the first place? Because you see, in your question, they mentioned to you that your cylinder is having a constant volume. Okay, so no matter what you do to your gas, your volume will still be the same. Let me just write it out for you. Why do I say that? Number one, you always remember that gas always occupies the volume of your containing vessel. Okay, so right now they told you your cylinder, your containing vessel is constant volume. So if your containing vessel volume is constant, the volume of gas contained is constant too, regardless of the pressure and temperature change to the gas. Okay, the pressure could change, the temperature could change, but the volume by itself should still remain the same because it will always occupy the volume of your containing vessel. Okay, so it's because of that I can actually say that my volume is constant, therefore no work done. So here I can say that my internal energy delta IE, change in internal energy, is the same as my heat supply. Okay, so I have these two relations now. Okay, so what I want to do from there is that I want to relate these two together, this one and this one. Okay, this one is saying to me change in IE, change in internal energy, is equal to the change in KE. The second one is saying to me that change in IE, the change in internal energy, is equal to heat supply. I can actually equate these two together, where then I would be able to conclude that your change in kinetic energy is actually equals to your heat supply, okay, which is now equals to 2,900 joules. Okay, so this change in kinetic energy that you're talking about is actually the change in KE for whole gas containing n molecules. Okay, so whatever KE change that you have, that is for n number of molecules. Okay, so right now the change in KE of the gas is 2,900. This is for n number of molecules. If you want to find the KE change of a single molecule only, it will follow that you just take the total KE change divided by the number of molecules. Okay, so your total KE change is 2,900 joules. Your number of gas molecules, you already found it from the previous question, is 1.9 times 10 power 24. So all you just need to do is you just sub in that value. You will get the answer as 1.46 times 10 power minus 21 joules. Okay, so that one will cover this particular question here. So for the next section, they are now asking you to use your answer in part 2, which is this one here, to determine the final temperature T in Kelvin of the gas in the cylinder. Okay, so now they want you to find out your final temperature T, okay, by using the answer that you have found right over here. Okay, so to do this question now, based on your answer here, you will now need to use this equation. Remember just now I told you cannot use this equation for this part, but you are supposed to use it for this part now. Okay, so here, the reason why you want to use it now is because what you found here, the increase in average kinetic energy of a gas molecule, is actually this part here. So you know this value, you know the value of K, you can subsequently find out your change in temperature, which would then give you your final temperature. Okay, so you use this equation. Ek equals to 3 over 2K delta T. The change in kinetic energy of a single gas molecule is 1.46 times 10 power minus 21. equate it to 3 over 2 times your Boltzmann constant, you will find out what is your delta T. The delta T is your change in temperature. Okay, so maybe I should just emphasize this. This is your change in your temperature. So change in temperature being 70.5 Kelvin here. Now you want to find your final temperature. If you look at your current diagram from before, if you are at 173 degrees Celsius, you're going to temperature T here. This one here is your temperature change. Okay. If I call this T1 and I call this T2, T2 is actually T1 plus delta T. Okay. You just take your temperature T1 here, 173 degrees Celsius, plus with your temperature change, you should be able to get your final temperature. Okay, but don't forget that your temperature is in Celsius. You need to change it to Kelvin. Okay, because whatever equations that you've been using for ideal gases now, this one usually relates to Kelvin temperature. This is the temperature change in Kelvin. Okay, so your final temperature being T1 plus your temperature change. Your temperature change is 70.5, but your initial temperature is 173 degrees Celsius. Change it to Kelvin by plussing with 273. Your final answer will eventually be 517 Kelvin. Okay, so that one is for this question. All right, so this one is okay. Okay, next one that you could look at is page 12. Okay, this is June 17 P42. Right? Let me just write the page number here. Next question, have a look at page 12. Okay, so here they mentioned to you that the pressure P and the volume V of an ideal gas are related to the density rho of your gas by this expression. P is 1 over 3 rho C squared. So from there, state what is the meaning of the symbol C squared here. This one is something that we just did. It's basically the mean square speed, okay, or average square velocity. Don't call it the square of the mean. This is definitely wrong because it's referring to this. Okay, so that part should be okay. Now then you move on to the next part. Use the expression to show that the mean kinetic energy of a gas molecule is given by this is the derivation of the equation, where K is Boltzmann constant and T is your thermodynamic temperature. So when you were deriving your equation for average kinetic energy, I mentioned to you, you always use two equations. The first one is actually PV equals to 1 over 3 NMC squared. Second equation is PV equals to NKT. You need to equate both of these equations together so that eventually you'll be able to get EK equals to 3 over 2 KT. But your current equation given to you is not in this form. Rather, it's in this form. You have P equals to 1 over 3 rho C squared. Okay? So what you want to do now is you want to change this equation into this form before you proceed with your derivation. Okay? So in the last lesson that I had with you, I mentioned to you that density, this one I have to write it somewhere. I mentioned to you before that density is actually mass over volume. So if density is mass over volume, this one refers to the mass of gas, which by right should be N times M. Because this one here, the N is number of molecules, and then the small m here is not mass of the gas, but rather mass of a gas molecule. Okay, so you want to find mass of gas, you need to take number of molecules, multiply them with the mass of a gas molecule itself. Then you divide by your volume V. Okay, so you divide by your volume V right over here. Okay, this one is volume occupied by your gas. Okay, so this is your expression for density now. If you sub it into your original equation, P equals to 1 over 3 rho C squared, you sub it in, you're going to get P equals to 1 over 3 Nm over V C squared. So you rearrange it, you will eventually get PV equals to 1 over 3 Nm C squared, which is what you want here. Okay, so from there, you use another equation, PV equals to NKT, equate both of them together, do whatever is necessary, until eventually you get 3 over 2 KT equals to half MC squared. So before you end it up, you always need to write this. Since EK is half MC squared, therefore EK is 3 over 2 KT. This is required to be shown. Your marking scheme specifically emphasize it. All right? So that is your derivation for this particular question. Then next comes the part where you look at B1. Okay? B1 is particularly confusing. You have an ideal gas containing 1 mole of molecules that is seated at constant volume. So keyword here, constant volume. Use the expression in A2, which is this one here, to show that the thermal energy required to raise the temperature of a gas by 1 Kelvin has a value of 3 over 2 your molar gas constant. Okay, so how are you going to show that the heat energy required to raise the temperature of gas by 1 Kelvin is this amount? Okay, so how do you know the amount of heat required to raise by 1 Kelvin 1 mole of gas? Not forgetting this one. Okay, your gas is 1 mole. They want you to find out what is the heat energy required to raise the temperature of that 1 mole of gas by 1 Kelvin. Show that it's equals to 3 over 2 R. Okay, so this one would require you to again do some basic derivation. So the first thing you could always do is you look at your thermodynamic first law definition again. Delta U is delta Q plus delta W. Because you see that your volume is constant, delta W is 0. Therefore, delta U is delta Q. Internal energy increase is equals to heat supply. Then second thing you do is you look at the definition of internal energy. IE is KE plus PE, but because ideal gas has no PE, so IE is really just your KE. So change in internal energy is change in your KE. So now what you do is you equate these two together. You will get a conclusion saying that heat supply is actually equals to the change in kinetic energy of your gas molecules. So this one not forgetting again. Is the change in KE of whole gas containing N molecules. All right. So to find the change in KE or whole gas containing N molecules, it was already mentioned to you earlier in the first part of this lesson. Take number of gas molecule, multiply with the change in kinetic energy of a single gas molecule. Change in kinetic energy of a single gas molecule in turn is this one, 3 over 2k delta T. Okay. And then your number of molecules N is your number of moles times with your Avogadro constant. So if you sub everything in accordingly, this is what you are going to get. Your delta Q is N times NA times 3 over 2k delta T. Okay, so now you try to sub in what you can. you already know that your number of moles is 1. Your Avogadro constant, you don't sub in first. The 3/2 remains as it is. Your temperature change is supposed to be 1 Kelvin. Okay, your K and your Na, you notice that I did not do anything with your Boltzmann constant and your Na. Although I know the values, I did not sub them in. There's a reason for that, because you see your final answer requires you to express them in terms of R. Okay, in terms of your molar gas constant, but your current equation has nothing to do with R right now. So you have to do something to somehow change them so that they're equals to R, so that there's an R inside. Now, if you recall from your ideal gas notes first page, Boltzmann constant is actually the ratio of two other constants. It is actually R divided by Na. Okay, if you recall back the notes first page, I mentioned to you Boltzmann constant is defined as R over molar gas constant. So right now, what you do is that you use this equation for Boltzmann constant, sub it in, all right? So K is now going to be R over Na. So from here, you will now see that the Na here will cancel the Na here. There was no need for you to sub in your value for Avogadro constant in the first place. You can actually cancel them off now. So your entire expression now, you will see is only left with R, which is what the question eventually wanted. So you simplify everything, you get delta Q is 3/2R. Okay? So that is for this question. There is a subsequent part to this question. Now, if you look at the next one, under B2, all right? So here in part 2, nitrogen may be assumed to be an ideal gas. The molar mass of nitrogen gas is 28 grams per mole. Use answer B1 to calculate a value for the specific capacity in joules per gram per Kelvin at constant volume for nitrogen. Okay, you want to find out your specific heat capacity for nitrogen gas now. Okay, so let's consider this. They ask you to use your answer in B1. Okay, the answer in B1 that you found was that the heat supply of 3/2R is to raise the temperature of 1 mole of ideal gas by 1 Kelvin. Okay, this is the required heat energy to raise the temperature of 1 mole of ideal gas by 1 Kelvin. Okay, so since this one here relates to specific capacity inside your question, you would know that the only thing that relates specific capacity that you've done so far was this. Q is MC delta T. Okay, so C is your specific capacity. To be able to use this equation, you need to know what is Q. You need to know what is your mass. You need to know what is your temperature change. Okay, but let's just consider this now. If you're talking about for 1 mole, your Q is actually 3/2R. And then your M here must be for mass of 1 mole. If you look at your question earlier, they told you that the molar mass of nitrogen gas is 28 grams per mole. This one already tells you that for 1 mole of nitrogen, mass is actually 28 grams. So now, if you're just considering 1 mole itself, you already know the mass is 28 grams. Okay? And the heat supply of 3/2R here was specifically just for raising a temperature by 1 Kelvin. So now you know all three of this. from which you can now find out your M. Okay, so now if you want to write out your workings, you'll probably be something like this, where you say Q is MC delta T, delta Q is MC delta T for 1 mole, is 3/2R. Your mass is 28 grams. You need to change it to kg. So it's 0.028 kg. Then multiply with C, multiply with 1 Kelvin. Eventually, your specific capacity would be 445 joules per kg per Kelvin. Okay, so that is for this particular part of your question. Okay, so this one should be done already. Just have a look at page 3 now. This is November 15 P43. So for this particular question, they mentioned to you that you have an ideal gas that is said to consist of molecules that are hard, elastic, identical spheres. State 2 further assumptions of the kinetic theory of gases. So when it comes to the assumptions of kinetic theory of gases, you already have them listed out in your notes under page 2. The ones that you generally use as your answer is actually the one in the second table. You generally would use the answers from here, not the one from the first table, because the first table is actually the most basic one. The one more specific to kinetic theory of gases is the one on the second table. So you have no intermolecular forces. Total volume of gas molecules is negligible compared to volume containing vessel. The molecules are in random motion. The collisions with each other in the walls are elastic. And lastly, time of collision is negligible compared to time between collisions. Okay, so these are the 5 possible answers, but one of them is actually unusable now. You actually cannot say this. If you look at your question carefully, they already mentioned to you that your molecules are hard elastic spheres. That really implies that your collisions are elastic. Okay, so this one here, the moment they mention to you that you are having elastic spheres, so collision is already implied to be elastic. So you will not use this answer from your notes. You won't say that the collisions are elastic because it's really stated by the question itself, or rather implied by the question itself. Instead, you use the remaining 4 answers, where you say is no intermolecular forces, volume of gas molecules is negligible compared to that of the containing vessel, time of collision is small compared to time between collisions, and then lastly, molecules are in random motion. Either one of these would be acceptable. Okay, this one, this one, this one, and this one. Okay, so just choose any one of them. And next question. So number of molecules per unit volume in an ideal gas is small n. This one you need to be careful. It's not number of moles. This one, whenever you use small n, you always assume that it is number of moles, isn't it? You cannot assume it here now because it's number of molecules per unit volume. Now, if it is assumed that all molecules are moving with speed v, the pressure P exerted by the gas on the walls of a vessel are given by P equals to 1/3 nm squared, where m is the mass of one molecule. Now, explain the reasoning by which this expression is modified to give the formula P is 1/3 nm squared. So what has actually changed from the original equation to this equation now? The only thing that has really changed is actually this v squared here suddenly having a mean symbol there. Okay, originally you don't have the mean symbol. Now suddenly you have the mean symbol. So what's the reason why you suddenly have the mean symbol? You could actually just say something like this. Because in a real gas, there's actually a range of velocities. So the average of v squares is taken. So an example I can actually just kind of illustrate to you is basically what they're saying is that you have a number of gas molecules. This one here is assuming that all your gas molecules are moving with the same speed of v. But the actual one is that these molecules actually all move with different speeds. This one could be V1, this one could be V2, this one could be V3, V4, V5, and V6. So you need to use the average of the velocities. You use the average of the V squares. Okay, so that one is hopefully okay. Okay, next one, question C. The density of an ideal gas is 1.2 kg per meter cube at a pressure of 1 times 10 power 5 Pascal and the temperature of 27 degrees Celsius. Calculate the root mean square speed of the molecules of the gas at 27 degrees Celsius. Now, whenever you see your questions referring to root mean square speed, there's really only two equations that comes to mind. It's either PV equals to 1 over 3 nmc square or half mc square equals to 3 over 2 kt. These are the only two equations that have mean square speed inside. All right, here you want to have root mean square speed. You need to first find out your mean square speed. Okay, so you have to use either of those two equations that you have written at the top left-hand corner there. So in your case, you'll be better to use the first equation. It'll be better for you to use this one. Okay, because in your current case, they give you density. See, they give you the value of density of your gas. You could show that PV equals to 1 over 3 nmc square is actually equals to P 1 over 3 rho c square. So what do I mean by that? I'm just going to do the derivation here. Or maybe I'm just going to do it below here. PV is 1 over 3 nmc square. If you put it as P equals to 1 over 3 nm over V c square, this one, N and M, N is number of gas molecules, M is mass of a gas molecule. This one gives you total mass of gas. And then this one is basically just volume. All right. So total mass of gas divided by volume will give you density. Right. So this one can now be simplified to P equals to 1 over 3 rho c squared. Okay. So this rho is the density of the gas, which is now given by your question. So you want to use this. Actually, you don't need to do the derivation. The derivation, I actually did it right over here. I used back the original equation from the question where they told you that the number of molecules per unit volume is small n. So small n is actually big N, number of molecules divided by volume, which eventually will give me this one here. And then after that, all I just need to do is I needed to rearrange them to get back this, no? Okay, so all this step is unnecessary. You just need to know that P equals to 1 over 3 rho c square exists. Okay, marks are not given for you showing that it's 1 over 3 rho c square. The marks are actually for this part. Okay, so as long as you know P equals to 1 over 3 rho c square exists, you sum in the relevant values, your pressure, your density. You can now find out your mean square speed at 2.5 times 10 power 5. And then your root mean square speed is actually just you square rooting the answer. Your root mean square speed is now 500 meters per second. Okay, so this one is worth 3 marks. Then next one that you can do is part 2. Right, so if you now look at part 2, let me just erase off all this unnecessary stuff. Now you now look at part 2, you are now supposed to calculate out the mean square speed of the molecules at 207 degrees Celsius. You are not calculating root mean square, you're calculating mean square speed now. So in your case, right now, you would not be using the first equation anymore. Okay, you won't be using first equation here, because although this question is asking for mean square speed, we have two possible equations to use, but you cannot use the first one. The reason is because this one here involves temperature now. You see, the first equation here has no relation to temperature. And this one has no relation to temperature. That's why I do not use this. Instead, I will be using the second equation here, because you can see it has some sort of relation with temperature, and it also has mean square speed inside. So I will use this equation for my case now. All right. So you use half mc squared equals to 3/2 kT. From your gas, from state 1 to state 2, it was mentioned that your gas was originally at 27 degrees Celsius. Now your temperature is 207 degrees Celsius. So let me just write it out here. T1 was 25, was it? Sorry, 27. T1 was 27 degrees Celsius. T2 is now 207 degrees Celsius. So from T1 to T2, what is now your mean square speed? Okay, T1 would correspond to a certain mean square speed. T2 would also correspond to another different mean square speed. This one is the first mean square speed. This one is the second mean square speed. So they are now asking you for this second mean square speed now, when your temperature change from T1 to T2. So you use half mc squared equals to 3/2 kT. Now between state 1 and state 2, there are certain things that will remain constant. Your Boltzmann constant is obviously a constant, and then because you're using same gas here, your mass of your gas molecule obviously will be the same. So m and k are constant, therefore mean square speed is proportional to t. Okay, so your mean square speed 2 to mean square speed 1 is equals to T2 to T1. All right. Now, you will notice that this one I write the 1 and 2 inside. And then for the ones that I wrote in my actual work solutions, I write the 1 and 2 outside. It doesn't matter which one you write. You can write it inside, you can write it outside. It will be apparent to anyone who reads it that you're referring to state 1 and state 2. Okay, so you want to find out the mean square speed for state 2 is the ratio of the temperatures. Just remember to change your temperatures to Kelvin, because whenever you're talking about your equations for ideal gas, this one is always your Kelvin temperature. So you always need to remember to change it to Kelvin. So 207 plus 273 over 27 plus 273, giving you 4.5 times 10 power 5 meters square per second square. Okay, so that one would be for this particular question. All right.